Bismillahirrahmanirrahim. Assalamu alaikum. This is Dr. Nausheen Tariq Siddiqui, and I'm here teaching you Pharmaceutics, Physical Pharmacy, course number 315. Today, we are going to start our new topic, that is miscellaneous processes. We have already done some of the basic processes like distillation, and we are now going to do some miscellaneous processes that are required in the making of tablet formation, or certain times for the stability of the pharmaceutical preparation, or certain times for the ease of administration of that pharmaceutical preparation. So these miscellaneous processes are, although they are very easy and very short, but they are very important to remember. So you must remember all these processes by heart. These processes which I'm going to teach you are efflorescence, deliquescence, lyophilization, elutriation, excitation, ignition, sublimation, fusion, calcination, adsorption, decantation, evaporation, vaporization, centrifugation, desiccation, ligation, and trituration. As I've gone through, you must have noticed that you have already gone through many of the different processes yourself, and you know what they are, but we are going to study them in context of pharmaceutics and where we can apply, or where they are applied and how they are used, or they are not used, but they are kind of you want to get rid of these types of things, because certain times they become the side effects of, you can say, the non wanted part of a pharmaceutical preparation. Efflorescence is the number one method. Efflorescence is the loss of water of crystallization from a hydrated salt to the atmosphere on exposure to air. This is basically when you're making something and it has water of crystallization. So the loss of that water of crystallization from a hydrated salt is known as efflorescence. What are the example of hydrated salt? I've already given you when we were doing crystallization. I think you remember. If you don't remember, you must go back to that lecture of crystallization, and you again read that, and then you come and read this efflorescence, or listen to this lecture efflorescence, or any the other products. You must remember what you have already done, so that you can make a good connection between the previous and the new processes I am explaining. So the example which I gave you was sodium sulfate decahydrate, in which there are 10 molecules of water attached in their crystalline state. I have also given you the Epsom salt example, the magnesium sulfate, which has 7 water molecules attached. So the hydrated substances under normal condition exert vapor pressure due to their water of crystallization. What happens basically, these hydrated substances, they basically exert some vapor pressure due to their water of crystallization. They exert some pressure, and when this pressure, in crystallization as well and in this as well, the phenomena, or the basic of this phenomena is vapor pressure, which you have to keep in mind. What is the atmospheric vapor pressure, and what is the vapor pressure of the water molecules that are present in the substance itself. What are hydrates? Hydrates are solids that contain water molecules as part of their crystalline structure. They are what? Hydrates, which I've given you example, the sodium sulfate decahydrate. But it is they are basically hydrates which contains water molecules as part of their crystalline structure. The water in the hydrates is known as the water of hydration, or the water of crystallization as well. The combination of water molecules with molecules of a compound results in a hydrated form. A large number of compounds crystallize in hydrated form. Examples are Copper sulfate combines with 5 molecules of water, while sodium sulfate combines with 10 molecules of water. Magnesium sulfate combines with 7 molecules of water, while ferrous sulfate combines with 7 molecules of water as well. Presence of water of crystallization is not essential for crystal structure. This is not essential, but certain times when crystallization occurs, this water molecule, they also become the part of that crystalline structure, or you can say they are kind of trapped in the basic crystalline structure which is making. So it's their tendency, you know, to keep those water molecules, or the water molecules remain there, and the crystalline structure is makes around those water molecules. So the presence of water of crystallization is not essential. It's not necessary for crystal structure, as sodium chloride, potassium nitrate, and many other compounds have definite crystal structure without water of crystallization. What is the basic principle behind efflorescence? If the vapor pressure of the hydrated salt, now think, what is the basic principle? The vapor pressure of the hydrated salt is greater than the pressure exerted by the vapors surrounding the atmosphere, then the salt will attempt to attain equilibrium with its surroundings and will therefore tend to lose water to form a lower hydrated or an anhydrous salt. Means the vapor pressure of the water molecule which is inside of the salt is greater than the pressure which is exerted upon the surroundings. So it will tend to move out, or it will be displaced by the salt to attain equilibrium. Therefore, tend to lose water to form a lower hydrate or an anhydrous salt. This phenomena is called efflorescence. For example, the vapor pressure of washing soda is normally, this is sodium carbonate tetrahydrate, normally exceeds that of the vapor pressure in the atmosphere. These salts effloresce, that is, lose all or part of the water of hydration, and their surface assumes a powdery appearance. Hydrated cupric sulfate or blue vitriol, the aqueous vapor pressure of which is lower, undergoes efflorescence only if the air in contact with it is relatively dry. While cupric sulfate is, it is also called as blue vitriol, it only goes under efflorescence if the air in its contact is dry. A salt such as copper sulfate may form more than one hydrate, each of which possess its own definite vapor pressure at a given temperature. The following hydrates of copper sulfates are known, that is copper sulfate 5H2O, copper sulfate 3H2O, and copper sulfate H2O. When certain substances of low vapor pressure, such as calcium chloride, with water are exposed to air, they form higher hydrates. Such salts may be used in the removal of moisture from air or other gases. They are used certain times to absorb water from the air or gases, as they capture water from the atmosphere. Example is the pressure of water vapors in the atmosphere is about 13.3 into 10 square Newton per m square at 293. Okay, therefore, the hydrates with vapor pressure greater than this will show efflorescence and will be unstable. Those hydrates which have vapor pressure above this atmospheric vapor pressure, they basically will show efflorescence and will be unstable. If they have the atmospheric vapor pressure above this pressure, then they are unstable, provided that the lower hydrate forms still exert a vapor pressure greater than the surrounding atmosphere, of course. If this is not so, the water will be taken up from the atmosphere by the lower hydrates hydrates as fast as it is formed, and the final equilibrium will depend on the rates at which water is lost or taken up by the two hydrates. Basically, जिसका भी वेपर प्रेशर जो है वो ज्यादा होगा, वो इक्विलिब्रियम मेंटेन करना है ना बेसिकली. सो फॉर मेंटेनिंग दैट इक्विलिब्रियम, तो जो भी या तो सराउंडिंग का एटमॉस्फेरिक प्रेशर ज्यादा होगा या फिर हाइड्रेट का इटसेल्फ. हाइड्रेट का अगर ज्यादा होगा तो इफ्लोरेसेंस अकर होगी, वरना जो है वो जो हाइड्रेट है वो ही वाटर टेकअप कर लेगा. Okay. The behavior of various forms of sodium carbonate. इसकी example के लिए you have to see कि the behavior of various forms of sodium carbonate. The vapor pressure exerted by the decahydrate is much greater than that of the normal atmosphere, and it loses water by efflorescence and is converted to a monohydrate. The vapor pressure जो exert हो रहा है by the decahydrate is much greater than that of normal atmosphere, so it loses water by efflorescence and it is converted into monohydrate. अब यहाँ के बाद खत्म नहीं होती, आगे क्या है? The vapor pressure of it is still above that of atmosphere, but further apparent loss of water does not occur because the anhydrous salt is rehydrated at a faster rate than the dehydration of monohydrate. अभी भी वेपर प्रेशर ज्यादा है, लेकिन इस वक्त जो है वो अपेरेंट वाटर लॉस जो है वो इतना ज्यादा नहीं दिखाई देगा या सुझाई देगा, बल्कि क्योंकि डिहाइड्रेटेड जो वो है वो रीहाइड्रेट भी हो रहा होता है साथ में एट अ मच फास्टर रेट, तो हमें वो जो है डिहाइड्रेशन के बजाय रीहाइड्रेशन जो है वो नजर आती है. The vapor pressure of hydrated salts and therefore the rate of efflorescence increase with the rise in temperature. Next is deliquescence. Deliquescence में दो चीजें आपने याद रखें, hygroscopic and deliquescent. दोनों में फर्क क्या है? Hygroscopic क्या है? A substance is hygroscopic if it readily absorbs water from the atmosphere and forms a hydrate. Then it's hygroscopic only. When it is only absorbing water and it's from the atmosphere, then it becomes hydrate. While what is deliquescent? Deliquescent is a substance if it absorbs water from the air until it forms a solution. It actually, जैसे अभी मैंने आपको डेकाहाइड्रेट की मिसाल दी, उसमें it doesn't become a solution. It doesn't absorb until it becomes a solution. बल्कि वो क्या कर रहा होता है कि वो वापस जो है वो उसकी दोनों प्रोसेसेस चल रहे होते हैं, हाइड्रेशन एंड डिहाइड्रेशन या रिहाइड्रेशन दोबारा से हो रही होती है. लेकिन डेलिकेसेंट की जो एबिलिटी है उसमें ये होता है कि जब तक वो सोल्यूशन फॉर्म में नहीं आ जाता, जब तक वो एब्जॉर्ब करता रहता है वाटर मॉलिक्यूल. Both these terms are used to indicate that a material takes up water vapors from the atmosphere and is converted to a more hydrated form. In case of hygroscopic substance, the more hydrated state is still a solid, but in deliquescence, there is an eventual formation of a liquid phase that is a solution. Such substances are said to be deliquescent, and the process is termed as deliquescence. Very soluble salts such as calcium carbonate are often extremely deliquescent. In both phenomena, the final more hydrated state must still exert a lower vapor pressure than that of the water vapor in the surrounding atmosphere. Otherwise, a newly formed hydrated state will immediately lose water by efflorescence and revert to the initial state. There you can also see and say that it is also temperature dependent. If you increase the temperature, maybe the deliquescence will not occur. Thus, for a liquid phase to be produced by deliquescence, it is necessary that the vapor pressure exerted by the saturated solution of the deliquescent material should be less than that of the surrounding atmosphere. Deliquescent materials are substances, mostly salts, that have a strong affinity for moisture and will absorb relatively large amounts of water from the atmosphere if exposed to it, forming a liquid solution. Deliquescent salts include calcium chloride, magnesium chloride, zinc chloride, potassium carbonate, potassium phosphate, potassium hydroxide, and sodium hydroxide. Example of hygroscopic material include desiccated sodium sulfate, ammonium chloride, etc. For hygroscopic and deliquescent pharmaceutical preparations, specialized storage conditions are required. Application: owing to their very high affinity for water, these substances are often used as desiccants. These compounds are used in chemical industry to remove the water product produced by chemical reactions. These are the application of these type of materials. Next process is the lyophilization process. This is a very important drying process, which is often used in pharmaceutical industry for numerous preparations and in pharmaceutics and in pharmacognosy as well. Because plant materials are usually dried through this process. Lyophilization, what is lyophilization? A stabilizing process in which a substance is first frozen and then the quantity of the solvent is reduced, first by sublimation. We all know what is sublimation. Primary drying, which is the primary drying state, and then desorption, which is the second drying stage, to values that will no longer support biological activity or chemical reaction. A stabilizing process जिसमें क्या हो रहा है, सब्सटेंस को पहले फ्रीज किया जा रहा है एंड देन जो पहला ड्राइंग स्टेज है इट इज सब्लिमेशन, उसके बाद डिसॉर्प्शन हो रही है व्हिच इज द सेकंड ड्राइंग स्टेज. इसलिए की जा रही है ताकि वो जो बायोलॉजिकल मटेरियल है वो मजीद अपनी जो बायोलॉजिकल एक्टिविटी है या जो केमिकल रिएक्शन परफॉर्म हो रहा है तो वो ना हो. ठीक है. Basically it's a drying process, but it is used for the stabilizing purpose as well. What is freeze drying? I mean, what is the history of freeze drying? Freeze drying was first activity developed by during World War II transport of when they started the transportation of serum. So they developed this method during World War II. The main aim was to store the product without refrigeration and to remove moisture from the thermodynamic product. Of course, when you are sending or you are transporting certain material, the biological materials, you need a constant temperature and you cannot maintain a temperature during a war. So it was very much needed at that time that you devise methods which are good for you and which serve the purpose. So in history, we see that this freeze drying served the purpose to transport the serum, which was required in World War II. The main aim was to store the product without refrigeration. So the refrigeration was not required after we freeze dried the product and to remove moisture from the thermolabile compounds. Atlas in 1961 built 6 production of freeze drying cabinet for Nestle Group in Germany, Holland. What is the basic principle behind lyophilization? Lyophilization is carried out using a simple principle of physics, that is sublimation. Sublimation is the transition of a substance from the solid to the vapor state without first passing through an intermediate liquid phase. A solid should convert to a liquid, then should convert to a vapor state, but in sublimation, it is directly basically goes from the process is from solid to vapor phase. Lyophilization is performed at temperature and pressure conditions below the triple point to enable sublimation of ice. The entire process is performed at low temperature and pressure by applying vacuum, hence is suited for drying of thermolabile compounds. The concentration gradient of water vapor between the drying front and condenser is the driving force for removal of water during lyophilization. What is basically what is happening that at low temperature, how the temperature you are drying, because you are also applying pressure, which is vacuum. Due to vacuum, the product dries at low temperature, which usually requires high temperature, but due to the applying of pressure, the product don't require high temperature for its drying, so the product is dries at lower temperature, or dries, or whatever your final product or the requirement of your final product. The concentration gradient of water vapor between the drying front and condenser is the driving force for removal of water during lyophilization. Are the objectives of lyophilization process? To preserve the biological activity of a product. This is the main objective of lyophilization process, to reduce the product weight, to lower the transportation cost. It also, because the water is all the water is lost, or you take it out, so the product weighs lesser, so it is easy to transport that material. To extend the shelf life or stability, it is very important to extend the shelf life or stability. You see, because there are certain times there are materials which, if you will keep it in that way or in a moisture state, it will acquire bacteria, and it will be deteriorated before it ends its shelf life. So to extend the shelf life of stability, it is required to dry thermolabile materials, to eliminate the need for refrigerated storage, and to get accurate sterile dosing into the final product container. So this is the basic component of a lyophilizer. The lyophilizer are basically the chamber which is shown below. It is certain times it is like that, but it's not all the time. The lyophilizer is not like that, but it contains a tray, or it is also certain times it is directly connected to a round bottom flask or something, but there is always a condenser and there is always a vacuum pump there. The material, the cabinet where you can put your material can be the tray type, or you can directly put it in a round bottom flask, and you can attach to a condenser. So it depends what type of a lyophilizer you have. If it's a commercial lyophilizer, it ought to be big, and it will contain trays or something like that. Okay. And this is this is an open cabinet. There is a door, and you can close that door to make it vacuumed. What are the different steps that are involved in lyophilization? Fundamental processes steps which are involved in lyophilization are: number one, it's freezing. Freezing the product is frozen. This provides a necessary condition for low temperature, of course. When you apply vacuum to that frozen product after freezing, the product is placed under vacuum. This enables the frozen solvent in the product to vaporize without passing through liquid phase. The product is already freezed, and when you apply lower pressure vacuum, then the vapors inside the compound, they vaporize without passing to a liquid phase, a process known as sublimation. Number third is that you provide little heat. After providing this little heat, the frozen product, the sublimation, basically it accelerates. Number fourth is condensation. Low temperature condenses plates remove the vaporized solvents from the vacuum chamber by converting it back to a solid. This completes the process. And the lower temperature, it condenses plates, and condenser plates remove the vaporized solvents from the vacuum chamber. They basically pull out, or they take out the vaporized solvent, and the remaining portion becomes a solid again. That's how the process is complete. Freeze drying is similar. Freezing the product solution to a temperature below its eutectic temperature. Eutectic temperature basically it's a temperature where the compound is in its flowy form. Basically, it's not liquid, it's not completely solid, it's something in between, but it's something fluid. Decrease the shelf temperature to minus 50 degrees centigrade. Low temperature and low atmospheric pressure are maintained. Pheromones are used as refrigerator. For formation of ice crystals occur. The rate of ice crystallization define the freezing process and efficiency of primary drying. These were the essentials of freeze drying. Now the primary drying, we are taking up one by one. First, we see why we have done freezing. Now we'll see primary drying, what is sublimation. Heat is introduced from the shelf to the product under graded control by electrical resistance coil or circulating silicon. And during sublimation, what happens? That heat is introduced from the shelf to the product under graded control by electrical resistance coils or circulating silicon. The temperature and pressure should be below the triple point of water, which is 4.58 mmHg. The driving force is vapor pressure difference between the evaporating surface and the condenser. Easily removes moisture up to 98 to 99%. Is secondary drying. What is secondary drying? Desorption. The temperature is raised to 50 to 60 degrees centigrade and the vacuum is lowered about 50 mm of Hg. Bound water is removed, then rate of drying is low and it takes about 10 to 20 hours. It's not a very quick process. It requires time, but worth it. It's the time which it requires is very, very much worth it. This is the same process in a graphical form. You can see that first you lower the temperature of the product, you freeze or solidify a product. Okay, then with vacuum, you increase a temperature, a little temperature in while you freeze that. When you apply vacuum, then 90 to 95% water is lost. Remaining water, 5 to 10% is lost during when you in the process of sublimation. And during desorption, 1 to 2% more water is lost. Freeze drying product characteristics: sufficient strength honi chahiye unme, they should be uniform in color, sufficiently dry, sufficiently porous, sterile होती हैं वो, or free of pyrogens and particulates, chemically stable both in dry state and reconstitution. Why they are free of pyrogens and particulate? Because the formation of bacteria or virus, they require a certain temperature. So that's why, because this all process is under lower temperature, so the product is sterile and they are free from pyrogens and particulates. What are the advantages of freeze drying over conventional drying? Forms of wet material to be dried. Freeze drying whole liquid pieces powders, while conventional drying you need to you need to make your material in pieces, while in where you are doing a whole your freeze drying, then you can freeze dry whole all liquid pieces या powder भी कर सकते हैं. Dry shape and form, the shape is maintained when you freeze dry, while in conventional drying it gets shriveled. Appearance is nearly same. What you freeze dry, the appearance is usually same, while in conventional drying it's not like that, it's shriveled. And color is maintained while you freeze dry, while in conventional drying it is faded. Rehydration is faster in freeze drying, while in conventional drying it's very slow. Heat exposure which you give is usually around 0 to 150 degrees centigrade, while in conventional drying it's about 200 to 300 degrees centigrade. So you see how you can also take thermolabile substances. Oxygen exposure is very low while freeze drying. And in conventional drying, of course, you cannot avoid oxygen. Retain volatiles. Yes, it's very excellent if you use freeze drying, but in conventional drying, all the volatile materials usually uh, get out the compound. What are the advantages of lyophilization? Removal of water at low temperature. Thermolabile materials can be dried, compatible with aseptic operations. More precise fill weight control. Sterility can be maintained, and reconstitution is easy. What are the disadvantages of lyophilization? There is disadvantages as well. Many biological molecules are damaged by the stress associated with freezing, freeze drying, or both. There can be material, which do not require to be freezed. The product is prone to oxidation due to high porosity and large surface area. Therefore, the product should be packed in vacuum or using inert gas or in a container impervious to gases. Basically, when you are making sterile product, then when the pressure is low and when they just pass the process of drying, then you immediately put the cap and make it sterile. So usually these things do not happen, and you can avoid this oxidation as well. Cost may be an issue depending on the product. Usually it's not a very low cost process, but if depends upon your product. If your product have more value, gets more valuable after this process, then of course this cost is not an issue for anyone. It's a long time process. It's not a short time process. You need time for this process. Common lyophilized products which you use are pharmaceuticals. Large and small molecules are there. Bacteria, viruses, because to keep the bacteria for a longer time, or to keep the viruses for a longer time, so their pathogenicity are retained. So you basically lyophilize bacteria and viruses. You can also lyophilize vaccines, plasma, small zoological specimens, fruits. These are very famous nowadays that you see chips made of fruits. They are actually lyophilized basically. Coffee, flowers, water damaged documents. You can also lyophilize those documents which are water damaged. Application: pharmaceutical and biotechnology to increase the shelf life of products such as vaccines and other injectables. In food industry, to preserve food, very lightweight, to produce essence of flavoring agents. Freeze-dried fruits are produced. Culinary herbs are preserved. Instant coffee powder is prepared. Technical industries: in chemical synthesis, formation of stable products, and in others, flora and fauna preservation, recovery of water damaged books, and documentations. Some lyophilized formulations are amphotericin B, which is antifungal, and which is in the route of administration is IV infusion. Chlorothiazide sodium. These are diuretics and antihypertensive drug. These are also IV infusions. Cisplatin, this is anti-neoplastic agent, and it is in the form of IV infusion as well. Gemcitabine, this is also anti-neoplastic agent, and it is also IV infusion. And thiopental sodium, so it is short-acting anesthetic, and it is also used in IV infusion. The next process is the process of elutriation. Elutriation basically is the process in which you, as you can see in the picture, basically you do sieving. Sieving is for the molecules which are bigger than one, which are bigger and which you can see with your naked eye. In elutriation, basically you are again doing the size reduction. Basically, you are separating the powder or your powder material according to their size, but the size of the material is less than 1 micrometer. So you cannot see, and you don't have that types of sieves that you can do sieving and you do the size reduction. So for those type of molecules, you require a process, and this process is called elutriation. Elutriation is what? The size reduction, size separation, basically the separation of particles according to their size. This is a process, and this process you have you do it with not with gravity or something. You apply a certain pressure, or you apply a certain gas, or you apply a certain force or air to do this process. What is this? Let's see. Definition is elutriation is a process in which the particles of the fluid moves in a direction opposite to that of sedimentation. You know how sediments, particle sediments with the force of gravity. But in elutriation process, the fluid is moved in a direction opposite to that of sedimentation. In gravitational sedimentation, the particles will move vertically downwards while the fluid travels vertically upward. If the velocity of the fluid is less than the setting velocity of the particles, then the particles move downwards again, the stream of the fluid. If the setting velocity of particle is less than the velocity fluid, the particles will move upwards. Means when the elutriation is a process in which the fluid move कर रहा है वो in direction of the sedimentation, उस पे कर रहा है opposite to the direction of the sedimentation पे आप fluid move करा रहे हैं. Gravitational sedimentation में particle move करता है vertically downwards while the fluid travels vertically upwards. Usually क्या होता है gravitational sedimentation में पार्टिकल नीचे जा रहा होता है, फ्लूइड ऊपर की तरफ जा रहा होता है. जैसे आपने सेडिमेंटेड प्रोडक्ट्स में देखा होगा, आपने ये नहीं देखा होगा कभी भी फ्लूइड नीचे होता है. ठीक है. If the velocity of the fluid is less than the setting velocity of the particles, then the particles will move downwards against the stream of fluid. जब अगर आप इसको कहें कि अगर उसकी वेलोसिटी, आप जो उसकी अपवर्ड वेलोसिटी है उसको कम कर दें, तो वो पार्टिकल्स की जो सेटिंग की मूवमेंट होगी वो थोड़ी सी कम हो जाएगी या वो इफेक्ट करेगी. ठीक है. If setting velocity of particle is less than the velocity of fluid, the particles will move upward. और अगर velocity of fluid से कम हो गई उसकी velocity sediment होने की, तो बजाय नीचे आने के वापस ऊपर जाएंगे. That is the process of elutriation. In other words, small size particles will move upwards while the large size particles will move downwards, of course. Because they will have the smaller particles, the sedimentating property will be lesser. So the bigger particle will move downwards and the smaller particles will move upwards. So elutriation is a process of separation of fine particles from coarse particles. The particles can also be measured by this process. The air elutriation usually gives shaper fraction of small and large particles than water elutriation. Water elutriation is less, give you sharp results as compared to air elutriation. Apparatus used for elutriation. The apparatus used for elutriation process is called elutriator. There are two types of elutriator: gravitational elutriation and centrifugal elutriation. In gravitational elutriation, as you can see, the name indicates that the gravity is concerned. Gravitational elutriation, in gravitational elutriation, the fluid particles move downwards due to sedimentation, that is force of gravity, while the lighter particles remain upwards. While in centrifugal elutriation, causes the fluid stream to rotate under the high centrifugal force to suspended particles. They basically kind of move or rotate. These particles, which are too large to rotate with the direction of the fluid, separates out on the wall. You know, the bigger particles will start separating. First, in the elutriator. However, the fine particles move easily with the stream of fluid. The the finer particle will move with the stream of the air, and it will come out from the chamber first, and then the bigger particle will come. In gravitational, you will get the bigger particle first and the smaller particles later. Centrifugal elutriation is again of two types: Dirichlet classifier and Sharpless superclassifier. The Sharpless superclassifier is useful for high-speed separation of fine particle. It has a capacity of 50 pounds per hour and operates on airflow for about 100 cubic feet per minute at maximum speed of 5,000 RPM. Uses of elutriation. Heavy and light kaolin can be separated by this process because the particles of heavy kaolin move downwards and those of the light kaolin move upward. 5 grams of kaolin is taken with 70 ml of water containing sodium pyrophosphate. After 5 minutes sedimentation, 50 ml is withdrawn, and the process is repeated with addition of 50 ml of water until 400 ml is removed. 8 times withdrawal to obtain 0.25 gram of dry kaolin. Now, the next process is excitation. Excitation is a process of accelerating the rate of efflorescence by increasing the temperature in order to remove the water of crystallization from a hydrated salt. This is the process is the main process is efflorescence, but you provide heat. So the process of efflorescence, it gets accelerated. That process is called excitation of a material. It may be regarded as a process of efflorescence controlled and or accelerated, but is applied in cases where water is normally lost by efflorescence. Usually जो है वो इसीलिए use होता है efflorescence के लिए, but you can use it for other purposes as well. Excitation may be carried out by taking a weighed amount of the substance in a tart dish. You can also do it in a lab. If you'll be interested, we will do it in a lab as well. Weight of dish is subtracted from the weight of substance or dish or is auto-zeroed. It is then heated on a water bath, sand bath, or in an oven with continuous stirring until a constant weight is obtained and there is no further loss in weight. No further loss is weight in weight indicates that excitation has been completed and no further water loss can take place. Mostly a sand bath or air oven is used for this purpose. The principle involved in this process of excitation are same as those in the process of efflorescence. The temperature required to remove the water of crystallization is very important and varies by degree. For example, copper sulfate, when heated at 30 degrees centigrade, loses 2 molecules of water of crystallization, forming copper sulfate with 3 water molecules. At 100 degrees centigrade, it loses 2 more water molecules, resulting in copper sulfate with 1 water molecule. The last water molecule is removed at 200 degrees centigrade, thus forming anhydrous copper sulfate. Some excited substances are not necessarily anhydrous. For example, ferrous sulfate, when heated about 100 to 105 degrees centigrade, loses 6 molecules of water of crystallization. When further heated to remove the last water molecule, its decomposition takes place. Hence, ferrous sulfate with 1 molecule of water is called excited ferrous sulfate. If it is excited, is carried out under vacuum, then anhydrous ferrous sulfate can be obtained below 100 degrees centigrade as well. The examples of excited salts used in pharmacy are excited ferrous sulfate, excited copper sulfate, excited sodium sulfate, excited magnesium sulfate, excited sodium carbonate, excited sodium phosphate, and excited aluminum, etc. As excited salts are very hygroscopic, they must be stored in airtight containers. What are the application? Excited is carried out to get an anhydrous product required in the formulation of pharmaceuticals. After the removal of water, the bulk and weight of the drug is reduced and they can be easily administered, used in manufacturing. Potency of drug is increased after the removal of water, and after excitation, fine powder is obtained, which is easy to handle as well. That is all for today. Inshallah, we'll see our next processes in our next lecture. Thank you very much.